Let's do another example of Jefferson's method. So again, try this one yourself if you want before, because usually in class time I would say, okay, try it with your groups, try to figure out what divisor you get working. And also another thing you might be wondering, is there only one right answer or could there be multiple different divisors that work? And actually, yes, there could be a lot of different divisors that could work. It just really depends on the numbers. Like back in this one, 50 didn't work, 49 didn't work, and sometimes it's like comes down to like, well, 49.5, 49.6, maybe. But usually there's a full range of numbers that will work, and they all will generate the same answer. So my point is there is a unique solution to Jefferson's method, but there's multiple different divisors that will get you the right answer. So anyways, another thing is if you work together with your friends or if you form a study group, in Zoom or something, it makes this easier because you can work together in finding the right divisor. And usually, like in during a regular semester when we have lab meetings, um, students will work together in groups, and it makes it a little bit easier to find the divisor. But let's return back to the scholarship example. So in this case, we had 5 departments, and we were giving out 20 scholarships to each of the 5 departments. And when we did it with Hamilton's method, we came up with the standard divisor was 40. The standard quota was each of these. And then because it's Hamilton's method, we went to the lower quota, 6, 6, 3, 1, 2, giving out a total of 18 scholarships. And that was too few, so we gave out the surplus seats to business and religion. But again, with Jefferson's, we're not doing that. We have to, instead of doing that, we have to pick a new divisor. And again, since that is too few, we want to decrease the divisor so that the quotas go up. So for my guess as a modified divisor, I want to make sure to make that smaller. So that way my numbers get bigger since this one was too small. And that's kind of like in each iteration, if it's too small, you decrease it. If it's too big, you increase it. It's actually the same direction, if that makes sense. But anyways, if you don't really know, you can always just guess, but I'm trying to give you this guideline to make this easier so that it's not just a random process of guessing, but we can use some intelligence to uh, get to the right place. And now that we looked at it, maybe you're wondering, well, should this be 39.5? Every problem will be different. So just because over here it came down to decimal doesn't mean it will be over here. But let's just say we're going to guess 39 because that probably would, after seeing that previous example, it might be logical to think, okay, let's just make a very slight change. But a lot of times a slight change won't make a difference. And if you're wondering, is there a more, how would I know all of this? It really depends on the original numbers and the ratio to the divisor. So just a rule of thumb for you guys, the smaller the numbers are, the more you want to change the divisor. The larger the numbers are, the less you want to change it. Because with bigger numbers, a smaller difference will make a bigger impact. But with smaller numbers, a small change won't make as big of an impact, if that makes sense. But let's just say we guess 39. You'll see what I mean in that this actually won't change it enough. But again, this is all coming from my brain of having done these problems for many years of teaching this class. So I've been analyzing these things for a long time, and that's kind of why I can see these patterns. But I'm trying to communicate some of these ideas to hopefully make it a little bit easier. But let's go ahead and calculate each of the lower quotas. So again, what I'm going to do is I'm just going to do them all using my new guess, 39, and I'm just going to write down only the lower quotas in each case. So biology would still have 6. Um, business would also have 6. Religion would have 3. Art would be 64 divided by 39, and 80 divided by 39. So that would be 1.6 rounded down. So instead of writing all those here, I'm just being a little bit lazy and only writing down the lower quota because Jefferson's rounds down unanimously. So actually notice that there was no change using a divisor of 39, kind of as I was saying, because these numbers are a little bit smaller. A lot of times a small change won't necessarily make an impact. So, and then again, if you're still watching this and still trying to guess, you can now guess a new divisor. Again, pause at any time to see if you can figure it out, because that's really the thing I want you guys to practice right here is, can you find the right one? But what I would probably do is maybe make it a little bit more extreme next. Maybe guess 35 and see if that works. And again, rinse and repeat. 241 divided by 35. Oops. 270 divided by 35. 145 divided by 35. And each one of those I'm going to just write down the lower quota, 674, and then 64 divided by 35, and 80 divided by 35. 80 divided by 35 would give me 2.2, which would round down to 2. And it looks like 64, I did not type in the 4, leaving with 1.8 to round down to 1. And in the case of using a modified divisor of 35, this appears to work because that would add up to 13, 17, 19, 18, 20. And so in this case, I have found my suitable divisor. Also, a suitable divisor is just one that works. So I've been talking a lot about modified divisors. So every one of them is modified, but once I find a modified divisor that actually properly apportions it, then we have what we call a suitable divisor, and we're done because we have found the right apportionment under Jefferson's method. And in this case, you could try, say, 36 or 34. Those may also work and give us the same answer. But that's kind of what I was meaning about a range. A lot of times there's multiple different suitable divisors for a specific problem.